Hi again, everybody. It's Professor Sebastian working in our Calculus 3 class notes. We're on page 49. We're in section 14.3 on partial derivatives. And in this first example on this page, example 44, I want to remind you about implicit differentiation. Hopefully it's something you learned how to do pretty well, but hopefully this example will shake the cobwebs off a little bit. What we want to do is we want to use implicit differentiation to find the partial of z with respect to x if I'm given this implicitly defined function of z. So I don't see explicitly z equals a function of x and y. I see where I have z's scattered throughout, and I either can't solve for z very easily at all, or I can't do it, like in this case you really can't solve for z, or you just want to leave it with separate z's in there. But this one you really can't get it as z equals a function of x and y. That's not possible. So we have to find the implicit derivative of the partial of z with respect to x. So we're assuming that we have two independent variables, x and y. Z is our function, and that the partial derivative actually exists when we do this. Okay, so in other words, we're assuming that z equals f of x, y, and the partial of z with respect to x exists. So how do you do that? You take the partial with respect to x of both sides of this implicitly defined function of x and y. Okay, so you take the partial with respect to x of yz minus natural log z, and then you set that equal to the partial with respect to x of x plus y. So when I take the partial with respect to x of y times z, I have to use the product rule. So first times the derivative of the second, so y times the partial of z with respect to x, plus the second z times the partial of the first with respect to x, partial of y with respect to x. But remember, we're going to treat y like a constant. X you don't treat like a constant because you're taking the derivative with respect to x, partial with derivative with respect to x. And z is the function, so you don't treat that like constant. But you do treat y like a constant when you're taking the partial with respect to x. So the partial with respect to x of y is 0 because y is a constant. Okay, then I take the derivative of minus natural log z, and I have to do the chain rule here because z is an unknown function of x and y, so the natural log of something, the derivative of that is minus 1 over that something, in this case z, times the derivative of the inside, which is z, so times the partial of z with respect to x. So that's the derivative on the left-hand side, equals the partial with respect to x of x, which is 1, the derivative of x is 1, and treating y as a constant, partial with respect to x of y is 0. So what do I end up having? What I want to do is I want to do some algebra in 2 steps. I first of all want to get all the terms that have partial z with respect to x in them on the left side of the equation, and then factor out that partial z with respect to x. And any term that doesn't have partial z with respect to x in it, I want it to be on the right side of the equation. So what do I have here? I have partial z with respect to x times y, so I factored out the partial z with respect to x, and then times a minus 1 over z. So y minus 1 over z. There's nothing else left on the left-hand side. There's still the 1 on the right-hand side, so that equals 1. Just for a nicer looking answer, I'm going to find a common denominator here, which is z. So I get yz minus 1 divided by z. All I did was simplify this into one fraction by finding a common denominator, which is just z. And then I divide both sides by yz minus 1 divided by z. So if I'm dividing by a fraction, I invert and multiply. So that just becomes partial z with respect to x equals z over yz minus 1. Okay, now functions of more than 2 variables. The notation and the partial derivatives are all natural extensions of what we just learned for functions of 2 variables. So if I have more than 2 variables, the easiest way is just look at an example. Let's now say I have w equals a function of x, y, and z. And so let's say that function is x times the sine of the quantity y plus 3z. So now I can talk about the partial of w with respect to x, the partial of w with respect to y, and the partial of w with respect to z, because there are 3 independent variables, x, y, and z, and w is now my function. So the partial of w with respect to x means you treat any y and z you see as a constant. So partial with respect to x of x times the sine of y plus 3z, well, since y and z are constants, the sine of a constant is a constant, so that's like a constant times x. So the partial with respect to x of a constant times x would be the constant, which in this case is just sine of y plus 3z. If I want the partial of w with respect to y, Now I treat the x and the z as a constant. So x here is a constant, 3z is a constant. So I just leave the constant in front when I take the derivative with respect to y. So now I have to use a chain rule here. The derivative of sine is cosine of y plus 3z times the derivative of the inside. Well, taking the partial with respect to y, the derivative of y is just 1. 3z is a constant, so the derivative of that is 0. So the whole derivative of y plus 3z is just 1. So there's my chain rule applied. So then it's just x times cosine of y plus 3z. And then if I want the partial of w with respect to z, I treat the x's and y's as though they're constants. So this is a constant x, I just leave it in front. Take the derivative of sine, which is cosine of the inside without a derivative yet, is y plus 3z, times the derivative of the inside. So the derivative of the inside is the partial with respect to z of y, but y we're treating like a constant, so that's 0, times the partial with respect to z of 3z, which is just a constant times z, so that's just 3. So my final answer is 3x cosine of y plus 3z.